send you off into space, in essence. So because you're on the axis, it's more unstable to be repulsive than it is to be repulsive all perpendicular to that axis between two atoms anyways. So sigma star is higher than the pi star bonding situations.
Mr. Morgan.
Yeah.
If the sigma line is deconstructed, does that mean the pi lines would also become deconstructed?
Yep. Yep. All right, now we fill it in. Say it again. 1s2, 2s2. Keep going. 2p.
Did I say we was ready?
Okay. Ask two fundamental questions. Did we conserve the number of atomic orbitals, and is that the same thing as the number of molecular orbitals? So 1, 2, 3, 4, 5 times 2 is 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of atomic orbitals needs to be the same as the number of molecular orbitals shown. So this is your atomic orbital columns. This is your molecular orbital. This is general chemistry only. This is Chem 2. This is what we focus on here, molecular orbitals.
Surprise. The anti-bonding is considered its own. Like, I would imagine that only one of them exists at a time, so like, kind of imagine.
We're going to actually get them all together collectively with blue marker. So let's dump them into there. Can the 1s electronic character, don't draw this, contribute anything to the 2s sublevel? Can this atomic orbital contribute to the 2s? No. Why not? Don't overthink that. Because it's the first energy level and that's the second, right? But the 1 can contribute to 1 and 1 can contribute to 1. So I'll draw these lines to say what is the direction that this electronic character can contribute. Okay. We can do the same thing here. The 2s can contribute to the 2s. And then the 2p can also contribute to these 2p situations. So these dotted lines are just saying where can the electronic character of these atomic orbitals move into to create overlap, so constructive interference, or anti-bonding situations, deconstructive interference.
So, Mr. Morgan,
Yeah.
I have a question. You said the higher up you go, the closer they become. So wouldn't it be possible eventually that for like something with two different?
Yeah, I'm gonna give you an exception in like 5 minutes.
Okay.
Chill, Jason.
You should see Mia's face. Mia wants to cut me right now. She's like, ugh, I can't.
Don't erase that, please.
It's because you keep
Oh my God,
taking
do not
notes
raise
and
anything.
we're trying to keep up
Yeah.
and that's not.
You're doing a really good job.
No,
you haven't
What do
picked
you
up,
mean? You don't know what's going on our paper.
You haven't picked up a chair and thrown it yet.
Dude,
Can
we're
we
not
draw
violent
the
into
anti-bonding
Nobody's
heads?
crying yet. This is good. This
You don't
is
have to
good.
be
I didn't know
crying
we
on the outside to be
Yeah.
drunk. Yeah, you don't know what's going on
That's
on the
true.
inside.
Yeah. All right, let's take these electrons and these and dump them in. We cannot violate Aufbau, Hund's, or Pauli's exclusion principle, even for molecular orbitals. So one at a time. So what I'm saying is, why can we not do that? What did it violate?
something rule.
Which one?
The
Which one?
exclusion principle?
Off balance?
Pauli's. Pauli says no two electrons can be the same.
Pauli's exclusion. Jason was right.
Okay, well, the fact that he said Pauli's, I was like, I'm
Yeah.
wrong?
No two electrons can have the same set of quantum numbers. This would have spin up, the same shape, same orientation, etc. So we have to do this. Alright, so we take one from here, drop them in. We take the second one and the second one, and we drop them in.
What?
Yep.
Sorry.
It's not.
So
Yeah, you should
one
repeat
from
that.
here, come together, and then the second ones come together.
Okay.
So you have two, you have 4 electrons, we have 2, we have 4 electrons. We have to keep the same number of electrons. We cannot get any more, we cannot remove any. We have to have the same. Take one from the 2s, one from the 2s, drop them in. Take the second ones, put them in here. Okay. Same thing for the P. I'm going to do it all at once. So we have 4 and 4 is 8. So 1, 2, 3. Follow the marker carefully. Can I do this?
No.
Why not?
One
You're
of
right.
the other one.
I have to do this. Why?
Because there's not enough.
That's Hund's rule, right? Each degenerate orbital of equivalent energy has to have one electron of equivalent spin before you can go back and put in a second electron with a opposite spin. So 4 electrons in 4 makes 8. 2, 4, 5, 6, 7, 8. Okay.
Wait.
So you don't fill all of them.
Okay,
So-
so,
So
okay.
2, 4, 6, 8, 10, 12, 14, 16 electrons total. And each oxygen has how many electrons based on the periodic table?
6. Nope, that's not
Total.
6.
That's
That's
eight.
valence.
Eight.
No, wait.
6.
Just based on the periodic table, it has 8. 2 electrons each have 8. That's 16 total electrons. We have 16 total electrons accounted for.
My brain cells are being reallocated at this point.
Protons
Yeah.
You know?
equal electrons.
We just want
Eight.
total.
I was
Total.
thinking of like valence electrons. Okay, do me fair.
What? That's different.
I don't know, okay?
Now remember, our original question is this the most stable arrangement of electrons around oxygen, or is there another option? Formal charge gave us an indicator of what might be more stable. Now we can verify it.
Wait, we're gonna use that chart to explain.
We're just
No,
gonna do
no,
this.
no, that's Gen Chem. Don't look at the labels at the top.
No, that's not what I'm
What are you talking about?
There it is.
Okay.
That's what determines whether we have a single bond, a double bond, or triple bond.
The way that
This can be a whole number,
works out, like there is logic. to
Or-
it, like, actually.
a decimal.
Whoa, there's just
fraction.
a lot of colors going on right now.
I know.
Is this all an equation together? Or
That's just a formula. So to find out whether this is a single, double, triple bond, or 1 1/2 bonds, or 3 1/2 bonds, you need to do this calculation. So this is, the bond character is 1/2 the number of bonding electrons minus the number of anti-bonding electrons. Okay? So do this with me. Just walk with me in this step here. Bonding, yes or no?
Yes. No.
no,
So if I take 2
minus two
minus
gets
2,
zero.
I get 0, divided by half.
Zero.
Zero.
What about here?
What did you get?
That's 0.
What about here?
Oh, wait.
0 divided 0 times
2
1/2
minus
equals
2.
0.
I'm
Is
sorry,
0.
you said
It's zero comes true because it's
Well,
zero divided
well,
by
let's simplify this. What I'm trying to do is, if you look at only core electrons, it's a wash. 2 minus 2,
0.
2 minus 2.
Zero.
Core electrons don't matter. Okay, so is 2s a core electron? Not necessarily, but look, it's a wash. So if you're looking at, in essence, the valence electrons, everything above, that's really what this is for. The cores, you really don't have to worry about at all.
So all the suborbitals that are filled with
So,
both
Let me box the bonding. Bonding, what else out of here?
the pi.
The
P,
pi.
Okay, the pi's. And
The sigma.
the
sigma.
that you can
2, 4, 6, 8 bonding. Minus anti-bonding. I'll circle. 2.
4.
What do we do?
2.
That's a double bond.
So we don't do the 1s because they're
But those aren't bonded
Core.
together, so you still count them?
Wait, I need you to put the one
It's
on the
on the-
other side.
you don't
Yes.
add the 1s because
So this
they're
is, since that's anti-bonding and anti-bonding, we still have 2 electrons
Okay.
in anti-bonding orbitals.
It's
they
still,
don't have
it's
If
still
you only had
cancel
one,
out.
you wouldn't count it then? Or
You,
would you still
uh,
count it?
then you just say, where would it be? 2, 3.
Okay.
So you still would count that.
Okay.
And even if this was like this, you would still have 2, 4, 5.
So do you round up or do you round down?
Don't round.
You just
Wait,
say, okay.
Morgan,
But it's bonding, it's a
Wait.
singular.
I have a question.
Go for it.
8 minus 4 is 4. Half of 4 is 2, so we got the double one. Where are you getting the 1 and the 3 and the 3 halves?
That's just example.
Oh, I'm just making these up.
Oh.
So that you're here. But if this came out to be a 1, it's a single, a 3 would be a triple. What's this one?
So,
1.5 bond.
You can have
Oh, wait,
one and a
really?
half.
What's 5 halves?
Well, I mean, yeah, because you know how we did resonance,
What's
so
up?
it's a single and then a dotted.
What'd you
But
say?
that doesn't
2.5.
mean-
What'd you just say?
I said with the resonance, and we would have a single bond and then the like dotted bond.
What type of bond character? So this is a structure. This is the resonance hybrid structure. How much bond character is this?
1 1/3.
1 1/3 as a mixed fraction, as a fraction.
4 9
Sorry.
So you're doing it. So if you have 4/3, that would be 1 1/3 of a bond.
So then how would you get a half bond?
So if we did actually the molecular orbital diagram for this, the result should be 4/3. 4/3. 1 1/3. What'd you ask? Sorry.
How would you do a half bond?
0.5.
You'd have to have two.
I know how you get the number. How would you?
You'd have one double bond and one single
You're
bond.
not gonna have that. You're not gonna have that.
What
What do you mean?
Yeah, you'd have one double bond and one single bond instead
Yeah,
of one.
Like
right here
one-
we can
one
just,
bond
like
and
we
one
can get a
antibond?
third bond with a resonance structure. How would you
Like one
get to a
minus-
half bond?
2 minus 1?
Wait,
Oh my God, I know.
That, no,
Okay,
like,
right.
you have to draw a 1.5.
How would you draw a half bond?
Oh!
He's like,
Yeah.
yeah, you just get a half
There's
bond.
three
That's the
single
bottom.
0.5.
But then
I
there's
know
one
what-
bond.
Rachel, it's Lydia.
I know how to do the math.
Ew,
for it.
I
How
hate
you
that.
actually
You're just
draw
so
that.
crazy yellow.
Oh my God, that was a lot.
Sorry, I'm slow. I know. If you have this, just this general structure, and that's resonance, then you do the same thing that we did here, and just draw lines.
Oh, you okay?
Yeah.
Yeah.
You don't. In that situation, you would just say there's 2 locations that have a single bond and divide it by 2. Yeah. So just dotted lines are fine.
Okay.
Okay, I think we should end it.
Lord.
Molecular
that was a really
orbitals.
good to get to that.
This was molecular orb, oh my freaking
Now
God.
tomorrow.
Oh, tomorrow?
I
Wait,
need
what
to
did
show
we
you
just
some
go over
exceptions.
this?
That was molecular orbitals. And
That
bond.
was
And
molecular
bond
orbitals?
We
I-
did it. You did it.
Okay.
We
that's
did
fine.
it.
That
We
part-
did it.
That part is